Good day. Our next topic is all about quantile. When you say quantile, it is a score distribution where the scores are divided into different equal parts. There are three kinds of quantiles. First, the quartile is a score point that divides the scores in the distribution into four equal parts. Next, decile is a score point that divides the scores in the distribution into 10 equal parts. And lastly, we have the percentile is a score point that divides the scores in the distribution into 100 equal parts. Now, here are the quantiles for ungrouped data. Quartile for ungrouped data. You have the notation q sub k, which is k over 4 times n plus the quantity of 1 minus k over 4 nth score. So you just find the nth score on the data set of the ungrouped data. For example, the first quartile, 1 over 4 times n plus 1 minus 1 fourth nth score. Same is true with the second quartile. 2 over 4 times n plus 1 minus 2 over 4. And the third quartile is 3 over 4 times n plus 1 minus 3 fourths nth score, where k is the indicated quartile. K could be the values 1, 2, and 3. N is the number of cases. Decile, just similar to the quartile, but the divisor is 10. D sub k will equal to k over 10 times n plus 1 minus k over 10 nth score. Same is true with the first decile, 1 over 10, and the ninth decile will be 9 over 10. Okay, indicated values of your k will be from 1 to 9. And there again the number of cases. Percentile for the ungrouped data. You have the formula P sub k is equal to k over 100 times n plus the quantity 1 minus k over 100 nth score. So we have the first percentile 1 over 100 and the 99th percentile 99 over 100. Again, the indicated values of your k will be from 1 up until 99. Now, moving on, we have the types of absolute measures of variation. When we say measures of variation, other sources call it measures of dispersion. Now, a measure of variation is a single value that is used to describe the spread of the scores in a distribution. The term variation is also known as variability or dispersion. There are several ways of describing the variation of scores. First, absolute measures of variation, and second, relative measures of variation. First type of measure of variation is the range, denoted by the capital letter R. It is the difference between the highest score and the lowest score in a distribution. Range is the simplest and the crudest measure of variation. Simplest because we shall only consider the highest score and the lowest score. So for ungrouped data, you need to arrange it from highest to lowest or lowest to highest, either. So your R there is equal to the highest score minus the lowest score. Example, you have two groups of score distribution. Group A, you have 10, 12, 15, 17, and 25. For Group B, you have 15, 16, 16, 17, and 17. So your lowest scores for each group is 10 and 15 for Group A and Group B respectively. Okay, so the range of Group A, since our highest score for Group A is 35, for Group B is 30, the range of Group A is 35 minus 10, which is 25. For Group B, you have 30 minus 15. Therefore, the range of Group B is 15. Analysis. The range of Group A is 25, which is greater than the range of Group B, which is 15. The implication of this is that the scores in Group A are more spread out than the scores in Group B, or the scores in Group B are less scattered than the scores in Group A. Now, how about for the group data? You have this formula, R is equal to HS sub UB minus the LS sub LB. HS sub UB is the upper boundary of the highest score, while your LS sub LB is the lower boundary of the lowest score. Example, you have a range, or you have the scores of 50 students in mathematics achievement test. You have the first column there, which are the class intervals. Okay, 25 to 32, 33 to 40, 41 to 48, 49 to 56, 57 to 64, 65 to 72, 73 to 80, 81 to 88, and 89 to 97. Frequencies are 3, 7, 5, 4, 12, 6, 8, 3, and 2. So we just need to consider the lowest score, which is 25, found on the first class interval, and 97, of course, on the last class interval. So you just need to get the class boundaries. 25 minus 0.5 is 24.5. That will now be the lower boundary of the lowest score. And 97 plus 0.5 will now be the upper boundary of the highest score. You subtract 97.5 by 24.5, the result is 73. So the analysis is for the range of value. If the range is large, the scores are more dispersed, widespread, or heterogeneous. On the other hand, if the range is small, the scores are less dispersed. Properties of range. It is quick and easy to understand. It is rough estimation of variation. It is easily affected by the extreme scores. Next measure of dispersion will be the quartile range, or IQR, and the quartile deviation. When you say interquartile range, it is a difference between the third quartile and the first quartile. In symbols, we have IQR is equal to Q sub 3 minus Q sub 1. What are the properties of IQR? First, it reduces the influence of extreme values. It is not as easy to calculate as the range. It only considers the middle 50% of the scores in the distribution. Next, the point of dispersion is the median value. How about the quartile deviation? It indicates the distance we need to go above and below the median to include the middle 50% of the score. It is based on the range of the middle 50% of the scores instead of the range of the entire set. The formula for the quartile deviation is Q sub D is equal to q sub 3 minus q sub 1 all over 2. So for the interquartile range, you just subtract the third quartile by the first quartile. For quartile deviation, you just need to divide the IQR by 2. So quartile deviation for ungrouped data example. We have the values here 6, 8, 10, 12, 12, 14, 15, 16, and 20. So we need to arrange it from lowest to highest. We will solve for the first quartile, which is 1 over 4 times n plus the quantity 1 minus 1/4. You have 9 over 4 plus 3 over 4. That is 12 over 4, which is the third score. Going back to the data set, values arranged from lowest to highest. The third score is 10. So that is your first quartile. Now for the third quartile, you have 3 over 4 times n plus 1 minus 3 over 4. That is 27 over 4 plus 1/4. That is 28 over 4, or that is the seventh score. Based on the data set of values arranged from lowest to highest, the seventh score is 15. So again, your first quartile is 10, your third quartile is 15. To get the IQR, or the interquartile range, subtract the third quartile 15 by the first quartile 10. 15 minus 10 is 5. That is your IQR. For the quartile deviation, you just simply divide it by 2. You have 5 over 2, which is 2.5. Analysis. The amount that deviates from the mean value is 2.5. Here's the overall interpretation of the IQR and the quartile deviation. The larger the value of the IQR or the quartile deviation, the more dispersed the scores at the middle 50% of the distribution. On the other hand, if the IQR or quartile deviation is small, the scores are less dispersed at the middle 50% of the distribution. Take note, the point of dispersion is the median value. Here's the analysis. When the value of IQR and QD is small, the scores are clustered within the middle 50% of the distribution. On the other hand, the scores are dispersed in the middle of the distribution when the value of IQR and QD. To determine which group of distribution is more clustered or dispersed, you should compare it with another group of distribution, since there is no standard value of a small or large value of IQR and QD. So you need to be relative in terms of comparing which is more dispersed or which is more clustered. Next, we have the variance and standard deviation. When you say standard deviation, it is the most important measure of variation or dispersion. It is the average distance of all scores that deviates from the mean value. It shows variation about the mean. It is also known as the square root of the variance. Of course, variance, the most commonly used measure of variation. We have the formula here. Sigma squared is equal to the summation of the quantity x minus the mean, or mu, raised to n, all over the population size. Sample variance, you have s raised to 2, or sigma squared, equal to the summation x minus x bar raised to n all over n minus 1. Here are the steps for solving the variance of ungrouped data. First, mean value. Second, subtract the mean value from each score. Third, square the difference between the mean and each score. Number 4, get to the summation of the squares from step 3. And lastly, solve for the population variance or sample variance using the formulas. So again, take note, in order to solve for the variance that is only the square root of, or I mean, the variance is the standard deviation, I mean, is the square root of the variance. Next, we have the relative measures of variation. Once you already have solved for the variance, you can now find for the coefficient of variation. It shows a variation relative to the mean. It is used to compare two or more groups of distribution of scores, usually expressed in percent. The smaller the value of the coefficient of variation, the more homogeneous the scores are. On the other hand, the higher the value of the coefficient of variation, the more dispersed the scores are in that particular distribution. Formula, you have, or which is denoted by CV is equal to S over X bar times 100%. Your S there is a standard deviation. Next, what are the classifications of skewness? First, let us define the measure of skewness. It describes the degree of departure of the scores from the symmetry. When we say symmetry, we based it on the normal distribution. In graphs, that is the bell curve, okay? Or a parabola opening downward. The skewness coefficient, or SK, can be solved using the formula. Skewness coefficient is equal to 3 times the quantity x bar minus x tilde all over S. Your x bar there is the mean value, x tilde is median value. Skewness can be classified according to the skewness coefficient. If your coefficient is greater than negatively skewed. However, if it is equal to 0, then there is the performance of the students, but not the reasons about their performance. When you say positively skewed or skewed to the right, it is a distribution where the fin and tail of the graph goes to the right part of the curve. This happens when most of the scores are below the mean. Negatively skewed or skewed to the left. It is a distribution where the fin and tail of the graph goes to the left part of the curve. This means, or this happens when most scores got by the students are above the mean. Okay? Here are graphical representations. Positively skewed. Okay? The students who took the examination did very poor. Most of the scores are low. Hence, most of the students got scores below the mean value. Okay, we have this first illustration here, this one. That is positively skewed. Second illustration will be for the negatively skewed distribution. Okay, and of course, for a normally distributed, it is a parabola, opening downward. So when we say negatively skewed, most of the scores, if not all, are above the mean score. And of course, for normally distributed uh, data set of values, the scores are symmetrical to the mean, which means the left part of the graph will be exactly as the same as the right part of the graph or the bell curve. Example, find the coefficient of skewness of the scores of 30 grade 4 pupils in a 45 item test in science if the mean is 38.5 and the median is 35.25 with a standard deviation of 2.5. Substitute all the values there. You have the coefficient of skewness is equal to 3 times the quantity of 38.5 minus 35.25 all over 2.5. Simplify everything. You have 9.75 all over 2.5, which is approximately equal to 3.9. That is now your coefficient of skewness. S K is equal to 3.9. Interpretation. Your coefficient of skewness is positive, 3.9. The score distribution is positively skewed. Most of the scores are low or below the mean. Thus, the students perform poorly in the said examination. Describing individual performance. Okay, there are four types of standard scores. First, Z-score. Second, T-score. Third, stay 9, or this is what we call standard 9. And lastly, percentile ranks. When you say Z-score, it is used to convert a raw score to standard score to determine how far a raw score lies from the mean in standard deviation units. From this, we can also determine whether an individual student performs well in the examination compared to the performance of the whole class. We have the formula there for the population and the sample. Z is equal to X minus mu all over sigma. For the population, for the sample, we have Z is equal to X minus X bar all over S. Okay? Now, the Z-score formula is very essential when we compare the performance of the student in his subjects or the performance of two students that belongs to different groups. It can determine the exact location of the scores, whether above or below the mean, and how many standard deviation units it is from the mean. T-scores. Okay, there are two possible values of z-score. Positive z if the raw score is above the mean, and negative z if the raw score is below the mean. To avoid confusion between negative and positive value, use t-score to convert raw scores, okay, into standard scores. T-score is another type of standard score where the mean is 50 and the deviation is 10. In z-score, the mean is 0, the standard deviation is 1. To convert raw score to t-score, find the z-score equivalent of the raw score and use the formula t-score is equal to 10z plus 50. Stay 9 or standard 9. It is the word, the origin of the word is standard and 9. That's why we call it stay 9. A stay 9 is a 9-point grading scale ranging from 1 to 9, 1 being the lowest, 9 being the highest. It is easier to understand than the other standard score model. Descriptive interpretation of stay 9, 1, 2, 3 is below average. Stay 9, 4, 5, 6 is interpreted as average and the descriptive interpretation of stay 9789 is above average. Stay 9 is used to compare two or more distributions of data, particularly test scores. Estimate or compute probabilities of events involving normal distributions. Okay, here's an example or an illustration of the stay 9 table. We have stay 9 1, 2, 3, 4, 5, 6, 7, 8, 9. Percentage of scores below negative 1.75 or 4%. Description of that one, very poor. For stay 9.2, description is poor. Stay 9.3, below average, slightly below average. Average, slightly above average. And then for stay 9.7, considerably above average. Stay 9.8, superior. And of course, stay 9 is the description for that one is very superior. Next, we have percentile rank. A percentile rank indicates the percentage of scores that lies below a given score. Example, a test score which is greater than 95% of the scores of the examinees is said to be the 95th percentile. If scores are normally distributed, percentile rank can be inferred from the standard score. In solving percentile rank, use the formula PR is equal to C F sub B plus 0.5 F sub G all over N times 100. Your C F sub B is cumulative frequency below the given score. F sub G is the frequency of the given score. And your N is the number of scores in the distribution. Solving the percentile rank is tedious or needs a very long process. We can shortcut the solution using SPSS or Excel only. Okay. Steps: arrange the test scores from highest to lowest. Make a frequency distribution of each score and the number of students obtaining each score. Find the cumulative frequency by adding the frequency in each score from the bottom upward. Find the percentile rank in each score using the formula and result as indicated for your fourth column. Correlation. Again, this is for describing relationships between two or more variables. Correlation refers to the extent to which the distributions are linearly related or associated between the two variables. The extent of correlation is indicated numerically by the coefficient of correlation, denoted by R sub xy. It is also known as the Pearson product moment correlation coefficient in honor of its proponent Carl Pearson. The correlation coefficient ranges from -1 to +1. There are three kinds of correlation based on the correlation coefficients: positive, negative, and zero correlation. There are two ways of identifying the correlation between the two variables: using the formula and using the scatter point on a scatter plot. Positive correlation. High scores in distribution X are associated with high scores in distribution Y. Low scores in distribution X are associated with low scores in distribution Y, which means that as the value of X increases, the value of Y increases too, or the value of X decreases, the Y values also decreases. Negative correlation. Contrary to positive correlation, if X increases, Y could decrease. As X decreases, Y increases. Okay, zero correlation. No association between scores in distribution X and scores in distribution Y. No single line can be drawn that best fits to all points, or no discernible discernible pattern can be formed. Here's the formula of the Pearson product moment correlation coefficient. R sub xy is equal to A on the numerator, you have n times the summation of xy minus the summation of x times summation of y. All over the square root of n times summation of x squared minus summation or minus the quantity summation of x raised to 2 times n multiplied by the summation of y squared minus quantity summation of y raised to 2. Okay?